the previous lecture, based on various examples, we have seen the need for introducing a general principle to predict whether a process can take place in a particular direction or not. This generalization is provided by the second law of thermodynamics, which we are going to state in this lecture. We can state the second law in an axiomatic way, in a similar way as we stated the zeroth and the first laws. So the second law can be stated as Sommerfeld states. The first part of the second law of thermodynamics states that all thermodynamic systems possess a property which is called entropy. This property, entropy, is calculated by imagining that the state of the system is changed from an arbitrarily selected reference state to the actual state through a sequence of states of equilibrium, and by summing up the quotients of the quantities of heat dq introduced at each step in this sequence of equilibrium states, and this heat dq is divided by the absolute temperature. And in this connection, we'll also define what is this absolute temperature. So this is the first part of the second law. So to make sense of this, so what we are going to do is that we're going to introduce a new state property which is called entropy, and we'll later on see that it is denoted by S, and this S is evaluated by summing up the quotients of the quantities of heat dq introduced at each step, that is along the path that takes the system from some reference state to the actual state, and the absolute temperature. So what we'll do is that we'll later on show that S is dq over T, and we'll integrate from the reference state to, let's say, the actual state. So we'll get S1 minus S at the reference state is equal to this, and we can define the entropy in terms of the entropy at the reference state. So this is the first part of the second law of thermodynamics. But to arrive at this definition, we also first need to define what we mean by this absolute temperature, which we'll denote by capital T. So this we'll have to define in the process of arriving at this particular equation. So this is the first part of the second law. So the second part of the second law states that during real processes, the entropy of an isolated system increases. That means delta S of an isolated system will always increase during a real process. In the next few lectures, what we are going to do is that we are going to provide the so-called proof of both of these statements. By proof, we mean that we can reduce the above two statements to simpler, apparently evident assumptions which by their nature cannot be proved in turn. So clearly these two statements state the second law of thermodynamics, and there is no mathematical proof of this statement. So what we'll do is that to derive this equation and this particular equation, what we are going to do is that we are going to look at some simpler statements which cannot be proved in turn, and from those simple statements we are going to arrive at these two statements for the first part and the second part of the second law. Now, the simplest of such a statement is the Clausius statement. So the Clausius statement states that heat cannot pass spontaneously from a body at low temperature to a body at high temperature. Now, it is important to define the meaning of the word spontaneously. So spontaneously here means that except for the bodies that are taking part in the heat transfer process, there are no permanent changes of any sort caused by the process. In other words, we can state the Clausius statement as it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler body to a hotter body. To make sense of this statement, consider this diagram. So here is our hotter body at temperature TH, and here is the body at low temperature TL. So the Clausius statement says that we cannot have a device that operates in a cycle and extracts heat from this low temperature body and rejects heat to this high temperature body without having any work input. Therefore, this statement implies that it is impossible to construct a refrigerator that operates without work input. So basically what you have over here is this is a refrigerator which works with zero work input, and the Clausius statement says that such a device is not possible. So in other words, we can say that the Clausius statement states that the COP of a refrigerator cannot be infinity, so the coefficient of performance of a refrigerator must be always less than infinity. Another simple statement is the Kelvin-Planck statement, and we are going to use the Kelvin-Planck statement and the Clausius statement to arrive at the original statement that we have stated for the second law of thermodynamics. So the Kelvin-Planck statement states that it is impossible to construct a device that operates continuously, that is, in a cycle, to produce work by exchanging heat with a single thermal reservoir. To show this schematically, so consider this thermal reservoir, let's say at temperature TH, and we have a device that works continuously in a cycle, and this device, let's say, takes heat QH and produces work, and from the first law this work done in one cycle would be equal to QH. So the Kelvin-Planck statement says that such a device is impossible to construct because it is taking heat only from a single thermal reservoir to produce work while operating in a cycle. That means the Kelvin-Planck statement states that it is impossible to construct a heat engine that operates in a cycle and converts all the heat received from a high temperature reservoir to work. In other words, the Kelvin-Planck statement says that a heat engine cannot operate in a cycle with 100% efficiency. Therefore, the heat engine must reject some heat to some low temperature reservoir to perform work while operating in a cycle. And note that this part is important, that this device operates in a cycle, because so if you have a device that is not operating in a cycle, then you can extract heat from a high temperature reservoir and convert all of that heat to work. For example, consider that we have this piston cylinder arrangement where we have an ideal gas enclosed within this piston cylinder, and let's say the gas expands slowly and there is some work done by the system on the surroundings, and in this process we also add heat so that the temperature of the gas remains constant throughout the process. So essentially this is an isothermal expansion. of this gas. So in this particular process, this gas takes heat from one thermal reservoir and it converts all of that heat to work because there's no change in the internal energy of the gas. So it might seem that this process is contradicting the Kelvin-Planck statement, but this is not, because this system is not operating in a cycle. So when we talk of Kelvin-Planck and the Clausius statements, we are always looking at devices that are operating in a cycle. Now, the Kelvin-Planck statement can also be stated in terms of the statement by Ostwald, that is, it is impossible to design a perpetual motion engine of the second kind. What do we mean by this perpetual motion engine of the second kind is that a machine that operates in a cycle and also does work while taking heat from a single thermal reservoir, such as the one shown over here, and it is not possible to have such a device according to the Kelvin-Planck statement, and the Ostwald statement also says the same. And note that the first law expresses impossibility of building a perpetual motion engine of the first kind, and perpetual motion engine or perpetual motion machine of the first kind means that you can have a device that produces work output without any heat input, and such a device is impossible to make, and that is given by the first law. But the second law says that you cannot have a device which takes in heat from a single thermal reservoir while operating continuously in a cycle. Such a device produces work, and such a device is not possible to construct. Now, all these simple statements, the Clausius statement and the Kelvin-Planck statements, talk of what processes are impossible to realize, and there is no mathematical proof for these statements. These statements are based on empirical observations. So all the experiments verify that these statements are true, and no experiment has ever contradicted these statements. Therefore, we take them as the truth, and from these statements, which are simple statements, the Clausius and the Kelvin-Planck statements, we are going to arrive at the statement of the second law that we have initially stated. But before we do so, it is important to note that the Clausius and the Kelvin-Planck statements are equivalent to each other. So we can use either the Clausius statement or the Kelvin-Planck statement to arrive at the statement of the second law of thermodynamics that we stated in the beginning of this lecture. Now, to show that the Clausius and the Kelvin-Planck statements are equivalent, what we need to show is that if the Clausius statement is violated, then it implies that the Kelvin-Planck statement is violated. And we also need to show that if the Kelvin-Planck statement is violated, then the Clausius statement is also violated. And if we are able to show this, then we can use either one of these statements in our later discussion, because both of the statements are equivalent. Now, let us discuss this equivalence of Clausius and Kelvin-Planck statements. So first, we'll show that if we violate the Clausius statement, then the Kelvin-Planck statement is also violated. So what we'll do is that we'll consider a device that operates between two thermal reservoirs, one at high temperature Th and another at low temperature Tl. Now we have this device which is a refrigerator, which, let's say, takes in heat QL from the low temperature reservoir and rejects the same amount of heat QL to the high temperature reservoir without consuming any work. So essentially this is a refrigerator with infinite COP, or refrigerator which transfers heat from a cold body to a hot body and operating in a cycle without taking any work input. And clearly such a device violates the Clausius statement. Now, to show the equivalence between Clausius and the Kelvin-Planck statement, what we can do is that we can consider a heat engine that operates in a cycle, and this heat engine, let's say, takes heat QH, which is larger than QL, and it absorbs this heat QH from the high temperature reservoir and rejects it to a low temperature reservoir, and the heat that is rejected to the low temperature reservoir is QL. That is exactly the heat that is being absorbed by this refrigerator. Now, in this process, this heat engine does work in one cycle that is equal to QH minus QL, because from the first law of thermodynamics, this is what we get. And note that both of these devices that operate in cycle do not violate the first law of thermodynamics. Now, if you consider the net effect of both of these devices, so if you consider both of these devices combined as a single system operating in a cycle, then what we have is that if you look at the low temperature reservoir, net effect is that there's no heat transfer to or from the reservoir, because this device, the refrigerator, absorbs heat QL, whereas the heat engine rejects the same amount of heat QL to this low temperature reservoir, whereas the net effect of these two devices on the reservoir at higher temperature is that this combined system that is operating in a cycle takes in heat QH minus QL from this high temperature reservoir, and there is no heat transfer between this system, which is combined system of this heat engine and the refrigerator, with the low temperature reservoir, and the net result is that there's a work output which is QH minus QL. Now, clearly such a device violates the Kelvin-Planck statement, because this device operates in a cycle and takes in heat from a single thermal reservoir, and it produces work while operating in a cycle, and that such a device is not allowed by the Kelvin-Planck statement. So what we've shown is that if we violate the Clausius statement, then the Kelvin-Planck statement is violated. Now, to show the equivalence between these two statements, we also need to show that a violation of the Kelvin-Planck statement implies a violation of the Clausius statement, and this can be shown now by considering a heat engine. So recall that the Kelvin-Planck statement says that you cannot have a heat engine that operates in a cycle which takes heat from a single thermal reservoir to produce work. So such a heat engine is not allowed by the Kelvin-Planck statement. Now what we do is that we can have a refrigerator that operates between this high temperature and low temperature reservoir, and the work that is delivered by this engine, which is otherwise not allowed by the Kelvin-Planck statement, is fed in to this refrigerator that operates in a cycle, and this refrigerator, let's say, takes heat QL from the low temperature reservoir, and from the first law, this refrigerator will reject heat QH plus QL to the high temperature reservoir, and that's because the work done on the refrigerator is equal to QH. Now again, let's consider the combined system of this heat engine and the refrigerator. So this combined system, if you consider The net effect of such a system is that it operates in a cycle but does not take any work input. And what it is doing is that it is extracting heat QL from this low temperature reservoir, and note that this high temperature reservoir gives away heat QH to this heat engine but receives heat QH plus QL from this refrigerator. So the net effect is that this device, that is this combined device, it operates in a cycle and transfers heat QL from the low temperature reservoir to the high temperature reservoir without consuming any work. And clearly this is a violation of the Clausius statement. Therefore, we've shown that violation of Clausius statement implies violation of Kelvin-Planck statement, and we've also shown that violation of the Kelvin-Planck statement leads to a violation of the Clausius statement. Therefore, we conclude that the Clausius and the Kelvin-Planck statements are equivalent. Now what we are going to do is that now that we have shown that all these statements are equivalent, we'll use either one of these statements to arrive at the statement of the second law that we have stated in the beginning of this lecture. So we'll show that using these statements we can arrive at this first part of the second law and the second part of the second law. And to do this, we'll have to introduce the Carnot cycle, and that we'll do in the next lecture. So in the next few series of lectures, we are going to look at how we can arrive at this particular statement of the second law from the Clausius or the Kelvin-Planck statements, which are equivalent to each other.